I'd like to wait a minute before we start so that people can join in. All right, class. Welcome to the last lecture in machine learning for this semester. Um, Before we get into the material that we want to cover today, I want to remind you of a final set of announcements. And uh, yes, okay, so that's not really good. That's not good either. Okay, comes out. So can people still see my screen share because something just went blank on my side? Okay, good, thanks. Um, Things are a bit unstable today. With every lecture is a new, an interesting set of bugs, and today's is no less. And I've never seen this before. I hope you can still see the screen share because I'm okay. Good. All right. So a final set of announcements for today. The same as what we had last week in the last lecture, actually. Um, so homework 6 is due today. It involves implementing SVM, logistic regression, and an ensemble. That's the main bit of it. And um, I hope you've spent some time on it, and we've had lots of conversations about it in the previous lectures as well. The final project, the things are due on the 11th. The submissions, it involves submissions on both Kaggle and Canvas. And if there are more details on the Canvas page where you can submit things. Some of you have already started submitting, and you can do it anytime before the 11th. I posted an announcement clarifying a couple of things about the code submission for the project. And then there's the final exam. It covers everything that we've seen in the semester, and it's on December 8th. It'll be on Canvas. As I said in the message that I sent this morning, it's going to be available the entire day. You get to pick which 2 hours that work for which 2 hours work for you in the day. Uh, just bear in mind that once you start, the clock starts ticking, and we'll try. We're still figuring out the logistics of how to clarify questions and the easiest way in which we can be available for you and such things. And I'll send out another announcement about that as things get clarified. I posted a document on Canvas that just like just a review of the entire semester that you can use to kind of help you prepare for the exam. The exam will be mostly things that it will look like a Canvas quiz. Basically, it's a timed Canvas quiz where you can type in things, select in multiple choice questions and such things. Are there any questions about any of these things? The code submission. Uh, so let's see. Okay, so there is a um, comment about making manual modifications to the data. So I would suggest, okay, so I don't know what Edward's talking about. Is it same as Patrick or same as Ben? But I'll answer Ben's question first. Um, so the I would strongly recommend in general for the project and um, for anywhere you use machine learning out there, don't modify the training data files directly. In fact, my preferred solution would be to, when you download a training set or basically data sets, you make that file read-only so that you don't even accidentally edit that file. The reason is you want, so the data that you download is the data that is, that's the one that other people can also use to verify your code. So if you make copies, I think what you should do is, first of all, if you modify the data, you should justify why you modify it. Are you fixing bugs? Are you cleaning up the data and such things? If that's the case, then what I would recommend is, there are a few things you could do, and depending on the time that you have, um, you should you can either choose to do it automatically or not. So one thing you can do is any of these transformations that you do, clean up, and I see that you have cross validation, fold generation, and feature binning, and all that. In theory, is done by code, right? So what I usually like to do is I have a function called preprocess that takes the original data and does all the pre-processing in code, and then if necessary, maybe writes it to disk somewhere. The advantage of doing that is this pre-processing is now documented in code. Of course, it's not great to think of code as documentation, but at least that is there. If you can do that, I strongly recommend it. Like your feature binning, it's not that you did the feature binning by hand for every example. It was all done by code. So wrap all of that into a single function called preprocess that you call once at the top of your shell script, maybe, and checks if that particular function can check if the preprocessed data is already there. If it is, you don't do anything. If not, you just do the preprocessing. If you so instead of merging it, I would suggest just submit both code. I don't want to get into a situation where everyone's working on different code bases. The problem really is that one of the problems is that Canvas will, I think, prevent you from uploading large data files. Ben, if you have specific questions, we can take this discussion offline. Edward, if this has clarified things for you, that's great. If not, we can also move this offline. But in general, I strongly suggest don't modify training code because training data or any data sets, because data sets are important artifacts that if for example, I'm not saying you did this, but there is the risk of you accidentally making the task easier or accidentally making the task unrealistic. And if you, or maybe you have made some assumptions in the modifications that you have done that needs to be documented somewhere. So it's always safe to do that in code. Let's go back to the question from Patrick. Oh, yes. So in logistic regression, does the learning rate get multiplied by both the loss and the regularizer? You mean the gradient, right? So the gradient, so you have, for logistic regression, you have something like the loss. Plus regularizer, and you take the gradient of this whole thing, and you now say that the weights is weights minus this, and you have some learning rate. Let's call that gamma t. So yes, because when you take the gradient, the gradient of a sum is the sum of the gradients. So you're right, it does get multiplied to the gradient of both things. If you use an ML, so another question is if you use a machine learning library to create a new feature set, would that count as a different learning algorithm? The external library restriction only applies to the algorithm itself and not the feature extraction. I'm thinking of feature extraction and pre-processing as just pre-processing. So it doesn't count as a external library. All right. Any other questions? Is the loss not calculated? No, so the loss is calculated using the entire thing. So the question is the loss not calculated using the entire objective, or do we exclude the regularizer? It's the entire thing. So this came up, I think, in office hours also the other day. When I say loss for this thing, it's unfortunate because it's really the whole objective. It's the whole objective that is being optimized. And this is the objective that's getting, so it's really the regularized loss. Can the cross-validation and the main run be separate scripts? Yes, you can make it separate scripts. Also include a README file that just says, tells me how to run things. The thing is, I need to know how to run your code. And you shouldn't make it too hard for me. In the spirit of replicability of machine learning code, you should, in theory, a trivial version of replicability is you just give me all your code and say, go figure. That's of course kind of evil. So what I would like is for you to kind of guide me through how to run your code. And it should not be that I should write code to run your code. So I should make it as easy as you can. I can copy and paste two things. Make it, if it's not in one file or one directory, upload all of those things, put a README somewhere that tells me how to go to each of these things and explains how I should run it. As assume that I can run code, but not necessarily, I don't want to go into your code and change hard-coded things, hard-coded directories, for example, if it's customized to your file system. So, write a README, upload a README that is going to be helpful. All right, any other questions? SVM over trees takes a long time to run, and even when it's coded with NumPy. Yeah, so this is also a discussion that came up in Canvas. So SVM over trees, one thing that you can do is you can first freeze the trees. So find a good depth for the trees, freeze it, treat it as pre-processing, write it on disk, and then take now essentially what you have is essentially a feature transformation. You have taken the original data, transformed it through some trees. You've transformed the training set, you've transformed all the cross validation folds and the test set, and now it's just standard SVM. So the tree stuff has to be done only once. You don't need to, as an optimization, in the interest of time, I suggest don't cross-validate over depth and C. So remember, for SVM over trees, you have depth and C and any other, I can't remember now, other hyperparameters. These things are for the tree, and this is for the SVM. So in theory, if you're going to do cross-validation over everything, you're going to take the cross product of depth and C and everything else, and that's going to take a fair amount of time because your innermost loop or one of your inner loops has the training over different trees. Instead, what you can do is first figure out a good depth using cross-validation. Stop training the trees at that depth upfront, and freeze the depth, and so train the trees on the training set using the strategy that's described there, and pre-process all the data and save the training the cross validation and the test splits in the new data format to a file. You can use a CSV file or liblinear or anything, and then you can now that that's done, at this point you just have another SVM experiment. Just run that. That should be a little faster. But yes, of course, it's going to take a little longer than standard SVM simply because SVM is, you're training all these trees. So that can't be avoided. How does C affect the training of trees and transforming the data? In theory, if you have, I've forgotten what depths I gave you. So let's say you have depth in say 2, 3, and 4, and let's say C in 0.1 and 0.01. Okay, 1, 2, 4, 8. I'm just going to use 2, 3, 4 because I've already written it. Let's say C is in 0.1 and 0.01 because that's all the space I have to write here. Now, in theory, I can think of this whole process of SVM plus trees and everything This is SVM plus tree that takes two hyperparameters, depth and C, and this cross-validation data and the training set, or even just the cross-validation data, meaning this is this, and this is all of these, and produces best depth and best C. It's possible where you do a cross product of everything and just find that, but that's kind of that's going to be unreasonably slow. So I don't know how it affects, but it could. I mean, there is a possibility that it could affect. Maybe if you use deeper trees, you don't want to. Okay, so here's an example. If D is large, that means the decision trees are going to learn more about the data. So you don't want to overfit using the SAM. So C could be small. If D is very small, then you want to use a larger larger C, for example. I'm just making it up. So to avoid this thing, so you can't just cache the trees because well, you can technically cache trees for all possible depths. So you cache trees for depth 2, you cache trees for depth 3 and 4, and then do cross-validation over C with that. You could do that. Another possibility is you first find the depth, the best depth, independent of any choice of C, using cross-validation, and you use the standard. So it would be literally just like cross. So first you find a. This would be like your homework 1. So you find, given a CB set and a depth, both of these go into ID3, and you get best depth. And now, given this best depth, you train 100 trees for this best depth. Now, once you find the best, based on this, then you can go and find the best learning rate and see for SVM, because you've trained 100 trees, those are frozen and cached, and you just find the. So this is to answer your question, Ben. You could do this by just doing this on the tree portion. This is a choice. Alternatively, you could do what Anthony described, where you cache all the trees for each depth, all 100 trees. And at this, when you're doing cross-validation, instead of running ID3 again and again, you just take those trees for that depth when you're seeing if that depth works with a certain C. Both of these are valid. In your report, describe what you've done. If you've already submitted your homework, just put a comment somewhere describing what you've done. This is an important point. When we do cross-validation with massive number of hyperparameters, there are like sometimes some tasks involve like about 100 hyperparameters. You have neural networks with all kinds of fancy tweaks on it, and you have to decide whether I want to use the tweak or not, whether you want to what depth of what's the depth of the neural network that you want to use, and what activation functions, what feature, what width of each layer, hyperparameters for things like momentum and Adam learner and all that. The point is, there are all these things interact with each other, and the standard strategy to do would be, I'm not going to do cross-validation or even validation holdout evaluation over the cross product of every one of these. Instead, I'm going to choose some of these and say, okay, I think these are really stable hyperparameters. And the choice of this particular hyperparameter choice is not going to interact with something else too much. That's a hypothesis. That's an assumption. That's a conjecture. And as a result, you're going to freeze them and then focus your cross-validation only on the rest. That's well-accepted strategy, and it's usually done. How do we know the best depth when we have not got to wait, hold on. So the Hans argument is the best depth cannot be independent from C and gamma 0. It could not be, but you can make an assumption that it is and see if it works in the interest of time. This is just a suggestion that I have in the interest of time, because in case you feel like it's running too long. Explain your strategy in detail. I think you will see that it maybe does not really matter. So there's probably less dependence on the depth and C and gamma naught than you might think. All right. I'm going to now switch to the lecture. There are a couple of things. I mean, today's lecture is all about high-level topics, and just one technical thing that I wanted to introduce, which I already promised in the last lecture, which is this bias variance trade-off. And it's already, so this is just terminology that you might come across when you read papers or any material involving machine learning. So let's talk about bias and variance. So every learning algorithm that you have, any learning algorithm, any strategy for learning that you have chosen requires assumptions. Essentially, the choice of a learning algorithm and a hypothesis space is just an assumption. So you need to start off by saying, I'm going to search over this class of functions. So your hypothesis space could be linear, could be a decision tree, it could be a neural network, it could be anything. Now, this choice affects, of course, how your classifier could be, but this choice also gives an upper limit of how the best classifier in this family could perform. Bias is the true error, the generalization error, if you want, or sometimes the loss of the best predictor in this particular set of functions you have considered. It's what is the, if an oracle had to do the optimization, had to do the search over the set of functions you've considered, what's the best it could do? It's in some sense, the upper limit of this particular hypothesis choice. So if, for example, the hypothesis set cannot represent the target function, it's worth thinking, would the bias be high or low? So the situation is the target function is something that's here, and you're searching over a set of functions that's here. Could the bias be 0? Like each of these, this is a function, right? So this is a function. You want to find that function. Every function has some error. Every functions here are classifiers. And the best classifier that you look for might be somewhere here. And of course, it's not going to be identical. There's going to be some examples where this function and this function disagree on. So the bias will be non-zero and possibly high. This is what we call as underfitting. When the bias is high, we call this underfit. We refer to this as underfitting. If the choice of hypothesis space that you have is not good enough to represent the concept. Another idea that's very related to bias is called variance. It's the performance of a classifier on this particular training set that you have. Maybe if you change this data set slightly, your classifier will change. So maybe if you take out one example and put in a different example, the model that you pick is going to change drastically. If that happens, that means really you're overfitting. So variance is how much it describes how much the best classifier depends on the choice of the training set, and overfitting is said to happen when you have high variance. Variance decreases when variance increases when the classifiers become more complex, because more complex classifiers can overfit. It decreases when you have larger training set, because it becomes harder and harder to overfit larger training set using simpler classifiers. So there's like an inverse effect between variance and the size of the training data. If you feel like this is too abstract, let me explain this using this sort of a game of darts. Imagine that our goal, we are throwing darts at this board, and our goal is to hit the center. The center represents the true concept. And every dart that we throw, in this case, every dot that we that will paint on the screen, is a different model that comes from a different data set. So when all your darts are roughly clustered close to the center, that means you have low bias and low variance. So they are tightly clustered. As a result, the variance is low, and they are mostly on target. When they are really off target but tightly clustered, that means that your even the best, most likely, even the best model is going to be far away from the center, is going to be far away from the target concept, and as a result, what you have here is high bias. Another extreme is when you have high bias and high variance, every data set that you choose gives you a different classifier, and these different classifiers are kind of spread all around. So it's centered around this thing farther away. So now, of course, there's another situation, which is low bias, namely, yeah, you are roughly in the region that you need to be, but you're overfitting whatever data set. So the hypothesis space contains the true concept, or contains a good enough representation of the concept. However, your the choice of hypothesis space is so complex, or maybe your training data is so small that changing the data set gives you a large variance. Bias and variance are not exactly the same as precision, accuracy and precision. And I'll talk about both of these things in a bit. In general, the error of a classifier, this is especially the analysis that's described here is mostly for, is largely for regression, but there's also in the context of some in the context of classification. The error of a classifier can occur because of bias, because of your choice of hypothesis space, because of the variance, because you're overfitting, and because of random effects like noise. When you have high bias, that means both training error and generalization error can be high. The classifier is not good enough to represent the data. High variance means that the training error could be low, but the test error or the test error is going to be high, or the test accuracy will be low. This means that the learning algorithm or the learner has overfit the training set using the hypothesis space that you have. So one perspective on machine learning is really we are trying to manage bias and variance. For example, ensembles reduce variance because when you combine multiple classifiers, you have this smoothing effect from the averaging. If you increase the depth of a decision tree, you increase variance, but you decrease bias. You increase variance because you can overfit. You decrease bias because you're making the model more expressive. With support vector machines and in general with linear classifiers, if you have feature transformations that are of a higher degree polynomial, then that increases variance because again, you overfit. But it decreases bias because you make it more expressive. Regularization actually increases bias and decreases variance. Lower complexity will, in general, reduce variance. Deeper neural networks will increase variance but decrease bias. Nearest neighbors, if you increase k, it reduces variance, but it increases bias because when you increase k, you get more. You can do more interesting things. Anyway, so every learning algorithm presents a choice that you have, or every hypothesis space presents a choice where you can kind of think about this choice as a trade-off between bias and variance. So it's complexity really. So this is there's a rich exploration of bias and variance in the statistics literature, especially, and it just gives a different perspective on the learning criteria that we have been thinking about, and it's a useful way to think about it. I'm going to switch topics slightly right now. I want to talk about some practical advice for building machine learning applications. And the bias and variance discussion is going to be useful because it provides useful language for us to talk about this. So in the entire semester, we've been looking at various machine learning algorithms and all these things. And today I'm going to talk about making machine learning work in the world, how to diagnose errors in your learning algorithm, any kind of analysis of errors, some thoughts about what you should keep in mind when you're injecting machine learning into something that you care about. And how do you make machine learning matter out there in the world? Most of this is based on experiential, me making mistakes and learning, really. But there's also fantastic stuff that's written by other people, and I have some readings on the class website if you're interested. So let's talk about how do you diagnose mistakes in your learning algorithm. So let's say you train an SVM, and let's say there are no bugs here. You've built an SVM classifier or logistic regression or neural network, pick your favorite, and of course you do all the right things. You use cross-validation for hyperparameters. You make sure that your training and test data are not contaminated. There's no overlap between these things and so on. And you find that your classifier is only 75% accurate, or depending on maybe your perspective, there's still 25% more to go. So the question is, what can you do to improve it? How do you make a model better? And this is a question that many of you also asked in the context of, say, your project. How do you make your classifier better? Now, this question might seem too abstract because there are so many things. the way to go about this is to kind of make it more systematic. There are many different ways to improve your model. You can add more training data if you have that luxury. You can use more features. You can use fewer features. You can use other features. Sometimes you might have to change your training. You optimize. You run your optimizer longer. You use a different learning algorithm, a different hypothesis space, or a different classifier, or you play with the regularization and such things. The problem is there are so many knobs that you can tune, and this can be tedious. And if you are not systematic about this, there will be interactions between these things, and you're really hoping that you find the right strategy. So one useful sort of thing to keep in mind is, how do you make this process a little more systematic? The first step is to solve a problem is actually to find the problem. So you need to first diagnose it. There are a few different ways in which things can go wrong. I'm assuming that there's no noise in your data. That's a way in which your thing can go wrong. But let's assume that your data is good. So you could be overfitting, and or in other words, you could have high variance. You could be underfitting. In other words, you have high bias. Your learning does not converge. You just gave up a little too soon, and your learning, if you had run it a little longer, your learning could your algorithm would actually maybe work. Or maybe you're not measuring the right thing. Maybe everything's working as well as it can. You're just not keeping track of the right thing. So let's maybe go through these things one by one. So first, how do you detect overfitting and underfitting? Just a reminder, an overfitting is when the training accuracy is much higher than the test accuracy, which means that the model explains the training set really well, but doesn't generalize to the future. Underfitting is when both accuracies are unacceptable, which means that the model is not even good enough to represent the concept. So when I say model, I mean the hypothesis space. So how do you detect overfitting or high variance? One way of doing that is to plot a curve that looks like this. On the horizontal axis is the size of the training data. You increase the data set. You add more and more data. On the vertical axis is the error. As you add more data, the training error goes up. That's a little peculiar because so the reason the training error goes up here is because if you have very little data, of course, any respectable algorithm is going to overfit it. So as you add more data, the training error is going to go up a little bit. The generalization error or the test error or the cross-validation error is going to go down. As you add more data, the model starts getting better and better. Now, one quantity to think about is, what is the gap between these things? If the test error keeps decreasing when the training error increases, but this gap is still too large, and by too large, I mean it is too large for whatever application you're working on in your domain, in your task, then this just means that the hypothesis space that you're considering is a little too complex. So this is a way of detecting complexity. You are overfitting, essentially. Ideally, both these things should kind of get, ideally, this thing should come down to this. So your generalization error should be close to the training error. But in practice, most of the examples I've seen in research code, for example, we see this gap because we do use heavily parameterized systems like massive neural networks, and they can actually end up remembering training data, and this is a problem. This is one problem. Another problem is how do you know whether your classifier is even good enough to represent the concept? Then you can plot the same two curves. So you on the horizontal axis, you still have the size of the training set. On the vertical axis, you have the error. And it seems like both of them, the model seems to converge, but this error is unacceptable. Even the best training error is pretty bad. That means your model is the family of classifiers you're considering, your hypothesis space, is not even good enough to represent the training set. So if this number is too large, then maybe you're not, you need to make the model, you need to consider a more complex set of functions, or you need to do something else. So essentially, you need to introduce more information into your system. You need to give your classifier a little bit more. So both of these curves tend to help, but notice that this is a rather expensive plot to build because this axis is the size of the training set. So in order to build this plot, you need to run your model to convergence on different fractions of the training data and then plot this curve. So, it's a rather expensive experiment to conduct. But what it tells you is if you have more, if you feel like there is overfitting, you can use more training data. You can use fewer features because more features can help the model kind of remember the training data. You could play with regularization, or maybe you just discard the features that you have and find other features. With underfitting, when your classifier is not good enough, you could, of course, use more features. You could use other features, or you could play with regularization. Playing with features tends to help with overfitting and underfitting. So there's a question. All of these curves seem to show some degree of overfitting because the training error is less than the generalization error. That's absolutely true, and that's unavoidable. All said and done, your classifier has seen the training data and it will remember something from it. Okay, so next, let's talk about how do you detect when your learner does not converge at all. So most of the learning algorithms that we have encountered are essentially something like optimization algorithms, where you have multiple iterations and you are essentially trying to minimize some objectives. So you should be plotting this curve where you are plotting the value of the objective as the iterations proceed. This is the curve that you're plotting for your homework. And you can, if you frame your learning as optimization, if the curve would look something like this. Somewhere in this region, you can say it's just by eyeballing it, you can tell that it's not converged, but somewhere here it has converged. We've had conversations about this even on Tuesday's lecture. But it's not always easy to decide whether learning has converged. For example, how do you know whether learning has converged here or not? Depending on your perspective of where you are, compared to this, it seems like it has, compared to this drop here, it seems like this drop is small. But if you zoom in, it seems like that's a rather big drop. So there's some amount of subjectivity on deciding when convergence happens. And the answer is, it's also a practical question. How much time do you have? But if you see something like this, if you see a learning curve that looks like this, where the objective is going up and down, something's wrong. We don't know exactly what's wrong, but something's definitely wrong because we are doing gradient descent. Well, it's not, I've written convex here, but that's assuming something like an SVM. We are doing gradient descent in general, which means we are trying to go down the surface, the loss surface, which means that the objective value has to go down. In stochastic gradient descent, the objective value will increase occasionally, but not so much that there is you see these wild jumps. If something like this happens, either there's a bug in your optimization code, or if you're using someone else's optimizer that has been debugged elsewhere, then maybe your learning rates are too large and your learner is just thrashing around. So if you have problems with the learner, you can kind of, you should really track the objective for convergence. That will help you decide whether you should run for more iterations, maybe even whether you should use a different classifier and such things. If you, yeah, I'm assuming that you're not using restarts, but even with restarts, you should not see wild jumps. This is symptomatic of something wrong. Another question that is another question that is something that really we tend to not think about is, are you measuring the right thing? This is an important question. Often we are given a task and we are told, like, for example, you have in your homework, say, I give you a task, I give you a data set, and I say, we're going to measure accuracy. Why do you take my word that accuracy is the right thing to measure? Maybe in this particular task, maybe in this particular domain, something else is a better metric. Maybe you should be thinking about evaluating the system in a slightly different way. Accuracy is just one way, and perhaps the most common measurement that you can make. But I'll give you an illustration of how accuracy can be misleading. Imagine you have a task where the positive examples outnumber the negative examples 1,000 to 1. If a classifier always predicts positive, it means it will get all these examples right and only this example wrong. Seems like your classifier is 99% accurate. It's really good. But has it really learned anything? You might think that this is a kind of a made-up example, but let me give you an illustration why this could be an important. This one negative example could be important. Suppose you the classifier is deciding whether, or instead of positive and negative, let's say your classifier looks at, say, a chest X-ray and decides whether someone has cancer. Most of the time, it will say that the X-ray is normal, but every now and then it will say, yes, it has cancer, and you really don't want to miss those things. So there are certain labels that you care more about than others, and accuracy does not really make a difference between these things. Maybe and sometimes you have unbalanced labels, and maybe you want to measure label-specific conduct label-specific evaluation. So, and the other thing to note is if you have such wildly unbalanced data, the baseline, even though you have two classes, the baseline of random guessing is not 50-50, but really 99.9 is to 0.01. So all of these things motivate thinking about other metrics. When you have unbalanced labels, it's a situation you might encounter. You measure what are called precision, recall, and F-score. Precision for a certain label is among examples with that particular label in the ground truth. Among examples that are predicted with that label. Your system predicts this label, say 10 times. So 10 predictions, 2 correct. Let's say 2 are correct. That means the precision is 20%. 2 out of 10 are right. Among the 10 predictions, so among the, let's say in the ground truth, in the data, there are only 2 correct predictions, but let's say there are 100 or 1,000 actual so let's say you have 10 predicted negative and 2 predicted negative, but there are 1,000 actual negatives and there are only 2 correct. This ratio is recall. So recall is among the given the ground truth label, what fraction of them are correct. So this ratio gives you precision, this ratio gives you recall, and these there's often this different algorithms or different models might lie in different places on the precision recall trade-off. So you can get 100% precision if you predict all examples have that label. Then of course you're going to cover these 10 also. You can get 100% recall if you don't predict anything. Sorry, if you I said it the other way around. You get 100% recall if you say that every example has label minus, which means you also covered these 1,000 examples that were actual minus, so you recollected everything. But your precision is going to be lousy. If you predict nothing is this label, that means among the ones that you predicted, all of them are right. So you get 100% precision, but that's your recall is lousy because you missed everything. Usually you want to balance both these things, and a way of balancing these two is called F-score, which is the harmonic mean. So it is really, 1 over F is 1 over P plus 1 over R. I think I made a mistake here, so there's half of this. So that you get you get a score that balances both these things, and often you will see F-score being reported as a balance between precision and recall. But these are not the only things. If you're solving a regression problem, you should not be measuring precision and recall and accuracy. You should be measuring squared error. So the task that you have decides what you should measure, and it's always important to think about whether you're measuring the right thing, whether the thing that you're measuring correlates with how the machine learning system is going to get used in an application. And that's a good segue into thinking about how machine learning fits into larger applications. As far as this class is concerned, we've been looking at machine learning. It's front and center. It's the thing that occupies the full screen, so to speak. But in practice, when we think of machine learning in deployment, it ends up being a tiny but important part of a larger software infrastructure. There are many other moving parts. There's an application, there's a task. So in your project, I asked you to think about just one more box, namely thinking about features. Some of you also did a little bit of interesting work around data collection, where you kind of played with cleaning up the data and such things. But there are other things. I mean, you might want to serve your machine learning system through some server. You need to monitor. Like any other software project, this becomes massive. So how do you keep track of these things? Machine learnings in systems is really going to be as big inside a software system, and if you're not careful with managing this particular important little box that fits inside, then in the future things can break. So if you're interested in this line of thinking, I recommend searching for this phrase, high interest credit card debt for machine learning. You're really accruing technical debt by not being careful with your system design. And Google has spent a lot of, and Google and Facebook and such companies have spent a lot of effort essentially trying to make their machine learning pipeline streamlined. One of the important things that we need to think about when we are thinking about machine learning in the context of a system is error analysis. How do we know how to improve unless we can think about where the errors are? There is a lot of other steps that go on. There's some data pre-processing. There might be some feature extraction. The feature extraction might itself be based on other machine learning methods, like your SVM over trees, for example. There might be data transformations. The data transformations could involve feature transformations, or it could involve cleanup, and all of these things interact with each other. And then there's the machine learning code itself. It's worth thinking about how each of these things contribute to the error. Error analysis is what tries to explain why a system is not working well, or well enough, or perfectly. One class of error analysis involves something called an ablative study, or feature ablation. Imagine that you have a really complex system that has many, many moving pieces. An ablation would say, let me just remove one of these pieces, remove these pieces one by one. And so there's an input, there's an output, and look at the impact of the output, on the output. And effectively, what it's doing is it's trying to explain the difference in performance between a strong model and a much weaker one. I'll give you an example of a feature ablation. Say you have a collection of features and your system's doing well, but you'd also like to understand why the system is doing well. And this is an important question. You can't just take a classifier at face value and assume that it's working. If it works well, it's doing it for the right reason. So it's worth understanding why it's working well. So what you do is you progressively remove some features and see which features, upon removing, led to the biggest drop. In other words, which features contributed most to the accuracy of the system. This will tell us what information the system is using. And some of you already done this, for example, for your project, and had conversations with at least a few of you about some interesting discoveries about the data. Which features is the system using? This kind of study is called an ablative study. So feature ablation helps us understand which features are important, but you can also do other kinds of ablation. For example, instead of using a 15-layer neural network with a certain architecture, what if I replace the whole thing and use maybe a 1-layer neural network, a linear classifier? How much does the performance drop? Effectively, what that tells you is how much quote-unquote non-linearity is in the problem. And this could help you understand something. Similarly, you can turn on or off different sources of information, and that will tell you how much that source of information is contributing. Notice that none of this really is technically tedious, technically difficult, but it's rather tedious. And this is one of the reasons why understanding machine learning systems is a massive computational effort. Just to kind of give you an example of how the machine learning today is really not just training a classifier and moving on. Let me give you show you this picture. This photograph was taken outside the CMU campus roughly around 2011-ish. And the question for you is, how many people are protesting in this photograph? You can type in the answers if you feel like it. How many people do you see here? So many of you are saying 4. Some of you are saying 5. When I counted, let me just okay. Now I can't see anything before other than 4 and 5 in my chat. But instead of counting people, let's say there are we have classifiers that detect heads of people. We have classifiers that detect hands of people, and we have a classifier that detects legs of people. So there are 2 heads. No, if you count this as a head, there are 3 heads. There are 3 hands, and there are 4 legs. Knowing what I know about people, at best, if you kind of naively just use these classifiers, at best there are between 3 to 4, about 3.5 people here. So something is problematic, because most of you said 4. I actually counted 5 because there's this one person here who is there, but you really don't see their face. But in any case, there are 5 people in this picture. So the point of this is, when we have a machine learning system, we don't really just use it in isolation. Machine learning systems interact with other software. They may, and think of machine learning as probabilistic programming, as programs that bake in some uncertainty. So such programs might interact with other programs which are deterministic or probabilistic, and we need to build a consensus prediction. In this case, we need to take all of these things and come to the number 5. So really, there's always a larger application in which we are going to be operating, and we can't just use the classifiers blindly. How do we? This is just a higher level systems view of machine learning. If you are interested in thinking about these kinds of how do you build consensus between multiple classifiers, we can talk about that in a different class. How do you? Next, I want to spend a little bit of time talking about just some advice really on injecting machine learning into some tasks that you care about. There are a few things to watch out for. Do you have the right evaluation metric? I already spoke about this, but I want to emphasize this point again. Before you decide on using the machine learning, which machine learning system you should use, what classifier, what loss, and everything, you need to think about how your system is going to get evaluated. The reason for that is you want to pick an evaluation that is independent of your learning system, because you want evaluation should really come from outside. So do you think about evaluation quite a bit? And once you've thought about that, you should also ask, does your loss function actually reflect the way in which your classifier or your system is going to get evaluated? You should be aware and beware of data contamination. Make sure that your training set is absolutely not contaminated by the test set, because once it is, that training set's useless. Learning is all about generalization to unseen examples. If your model gets to see the test set, if your learner sees the test set, in choosing model, that learner is not going to generalize. It's just going to remember the test set, and of course it will do well. So there's no point in it. There's no value in doing well on what you've already seen from the test set. In fact, I think you should not even be opening the test set files. Don't look at it. If you look at it, you accidentally might contaminate your model through your head. Another contamination that that's worth keeping track of, and it's easy to slip into your system, is you add a feature that is actually the label. This especially happens if your data is stored as, say, CSV files. and you accidentally use the column that corresponds to the label as a feature, and it seems like magic. At that point, you get a perfect classifier because, yeah, of course, you're going to get a perfect classifier. One of the features is the label. Any respectable learning algorithm will learn to copy that feature to the label. In general, I tend to be very suspicious of classifiers that are perfect because invariably that suggests these kinds of bugs. Be aware of the bias variance trade-off, or equivalently be aware of the trade-off between overfitting and underfitting. It's worth thinking about, whether you're overfitting your data set and trying to actively counter that. Countering that could involve, say, using regularization, using something like dropout, or using, say, better features, or using a weaker model. And while you're talking about these things, we've talked about high dimensional data sets a lot. In your homeworks, you're looking at hundreds of feature dimensions. There are problems where we work with millions of dimensions. When we are talking about high dimensional data, of course, we're not going to be able to draw pictures with high dimensional data. So invariably, we'll draw pictures that are in 2D. Don't just be aware of the curse of dimensionality. We spoke about the curse of dimensionality. The short version of it is that intuitions that work in low dimensions in 2D don't really necessarily work in high dimensions. So just keep that in mind and try to not, you need to, for example, if you're going to invent a new learning scheme and you're going to base that scheme based entirely on intuitions in 2D and hope that it works in high dimensions, just be aware that maybe it may not translate directly. Sometimes it does, sometimes it doesn't. We've talked about a lot about theoretical stuff in this class. Of course, the thing about theory is that it's only as good as the assumptions that it makes. So a theoretical guarantee is could be only theoretical. It may make invalid assumptions. For example, you may the theorem, for example, the perceptron Novikov theorem assumes that the data is separable. If the data is separable, then the perceptron algorithm will find a linear classifier. How do you know that the data is separable? Your theory might only be valid when you have infinite data, when you're estimating probabilities, for example, or with stochastic gradient descent. These guarantees are really in the limit as the number of as some number goes to infinity. In practice, you may not actually hit that. You of course are not going to hit infinity, which means that in addition to coming up with theoretical guarantees, you need experiments. Machine learning is an empirical science, which means you need to think about how to do experiments. You need to think about how to do experiments carefully. And if something works in theory but does not work anywhere in real data, then it's the data that wins. The theory might be beautiful, you might love it, you might have your career hinged on it, but if it does not correspond to real life, then it's the theory that has to go. Speaking of data, of course, I'm sure all of you have heard the buzzword about big data. Big data is not enough, but of course, more data is always better. More annotated data is, annotated data is like gold. So more annotated data is better. Cleaner data is great. And some of you might want to start thinking about, in your particular application of interest, in your domain, there's a wide representation of people from various backgrounds and various departments in this class. In your in problems that you care about, how do you build data sets? Building data sets is an art. And it takes a lot of effort and care and expertise to build it. So maybe you want to think about that. But in addition to building data, building data can actually be an expensive thing. One of the misconceptions that I want you to think about, I want you to know is learning is really, learning depends on the assumptions that you make. Learning is impossible without some kind of assumptions that simplifies search over functions, because learning is search over functions. Without these assumptions of regularity about nature, about the problem that you have, there is no hope for generalization. Learning requires knowledge to guide the learner, And there is no magic here. If there is one lesson that I want you to take from this class, it is that machine learning is not magic. What kind of knowledge? Anytime you choose, make a choice about a certain family of functions, a hypothesis space, about a model, you are essentially making a statement about the problem. If you say that you're going to use linear models, the statement that you're making is that you believe that the data is linearly separable. In your choice of a learning algorithm, you're still making some decisions. For example, if you use a stochastic gradient descent, as opposed to, say, one of the more fancier variants of stochastic gradient descent, like with momentum or such things, you're making a statement about the loss surface, about how it's not going to, there are certain properties. You can go back to the lecture if you want. Sometimes these choices don't matter, and sometimes they do. And it's worth understanding when they matter. And this is, again, knowledge that you bring in. Another place where knowledge comes into the system is in your choice of features. If you have the perfect features for the problem is as good as solved. So a lot of effort goes into feature engineering. Good features are worth thinking about. And once again, this goes back to understanding the domain, or at the very least, working with people who understand the domain. One of the fun things about working in machine learning is you get to interact with people who do such cool things in such interesting domains, because you have to work with them. Otherwise, you're just making maybe invalid claims about the problem that they're working on. Anytime you make these choices, these choices are all claims about the nature of the problem. And it's worth knowing whether this claim is good or not. Other advice, generally, I prefer starting off with simpler models first, because if it works, that's great. If not, at least they give you a baseline. And automatically, you bake in some sort of an Occam's razor style prior into how you are approaching the process. As many of you observed with your homework and also maybe with your project, ensemble seem to work better. It's a good tool to have in your toolkit. Another thing that's worth thinking about is your problem actually learnable? Is there even hope to apply machine learning? Because learning is all about generalization. If there is no hope for generalization, there's no point in using machine learning. A problem that is unlearnable is predicting what is the value of a random number generator. The problem is not learnable because it's truly random. You can try to build a classifier that predicts whether the next roll of my die is going to be a 5. It's not going to work because it's going to be as good as random. So learning is all about generalization to the future. And if you believe that there is no hope for generalization, then it's really not a learnable problem. Let's step up more a bit. In 2012, Kerry Wagstaff, who's a Utah alum, she did her undergrad degree here in Utah, then went on to do a PhD, I think at Cornell, and now works for NASA's JPL on really cool machine learning in the context of astronomy. She gave this talk in this conference, international conference on machine learning in 2012, where she spoke about these challenges that to the broader machine learning community, with the idea of making machine learning matter in the world. These are really interesting challenges. So, for example, number 5 here is, can there be a human life that's saved through an intervention because that machine learning systems brought in? Or maybe there is some sort of a decision-making process that machine learning has led or contributed to that saved $100 million. This was in 2012. Today, a lot of these things are starting to seep into our lives. Machine learning is everywhere. Data-driven machine learning or algorithmic decision-making is increasingly prevalent and involved in our lives. These are no longer just proof of concept, which means it's worth thinking about these broader questions about algorithmic decision-making. Do classifiers exhibit societal biases? How do we make sure that these kinds of systems that we have, the learned systems, these statistical, really complex systems that we are building, are transparent in their decision making. When should you leave? Is it okay to leave decision making entirely to a classifier? And if so, what if the classifier behaves in ways that are not ethically sound? Notice that each of these questions are not really not talking about loss. They're not talking about accuracy. They're not talking about any F score or such things. But these are, you can think of these as auxiliary criteria that are not tied to the thing that we optimize for. These are not the questions that I'm asking are not just, in the abstract. What if classifiers are used to decide how long someone should be sentenced to a crime? This is actually a thing that has happened. What if it decides whether someone's loan application should be approved or rejected? Once again, something that happens. Or even worse, I don't know what is worse, but what if it decides that someone should be fired? Once again, there are hints of such things happening. How do we ensure that these classifiers are not unethical or they are fair? In the context of, because these classifiers are involved in making decisions about people, how can we guarantee that it does not do any harm? And by harm, it could be a harm of representation, it could be a harm of allocation of resources, or it could be, harm in terms of decisions about people. How do we design algorithms which avoid discrimination? And what if the data itself, the data that you collect, or the data that you're given is itself unfair in its representation of people? All of these are questions that are important, open questions that the machine learning community, as a by and large, is trying to tackle right now. This is a kind of question where you may think these are very high level, and this is for someone else. Let me just build my classifier and write my code. And I think people like you who are starting to learn machine learning, this is the right time for you to start thinking about these questions, because you cannot think of introducing societal fairness as a band-aid on top. This notion, the study of fair machine learning has now become an important research question. It's an important societal question, and it's extremely crucial that we get this right, because it can have unintended consequences otherwise. Imagine, for example, that you have a job and a classifier decides to fire. And you could rationalize this by saying, of course, all classifiers are wrong. They do. The error of the classifier is only 1%. Let's say this classifier is 99% accurate, and you're that 1% that got fired, that where the classifier makes a mistake. Would that be a right thing? So the question that is worth thinking about is, how do we build statistical models that not just make predictions, but also expose how they make their predictions? So if you ask a human, for instance, and we started this class by talking about, can we introduce and learn how decision making can be automated, for instance. If you ask a human for a decision of firing or hiring someone, and they say, yeah, this person should be fired, you can always probe that person and ask why. We need systems that allow that in some sense automatically expose their decision making process and explain their decisions. So yes, making black boxes could be dangerous. I don't know if I don't know good or bad, but it could be dangerous. It could lead to unintended consequences. And there is more than enough evidence today to show that when we have classifiers that make decisions about people, it invariably makes decisions that are say unfair to groups of people who are underrepresented, and that's not good. So here's a challenge for all of you. How do you build algorithms that explain their decisions and at the same time learn? How do you build algorithms that maybe learn to explain? Open questions. There is some work out there that works on that talks about this, but really these are questions that we are, as a research community, grappling with. And unlike other kinds of research where these are just abstract academic things, they are actually going to impact people. Another thing to think about is, do we even have the legal frameworks to actually deal with these kinds of questions? And I mean, this is not a class on law, this is not a class on ethics, but I don't think we should leave ethics and law to other people. as computer scientists, we should think about this because we are the experts. If you understand machine learning, you should try to contribute to this law. I don't know how, but maybe there's room for updating laws to account for the fact that decision making about people is increasingly statistical and automated. Statistical, it always was. Automated makes it weaponized. Um, what if, for example, evidence is faked by just sampling from a generative model? And this is not even an abstract problem. This is a pressing concern. What if, for example, an automatic a self-driving car gets involved in an accident? Who's to be blamed? Should the person who trained the learning algorithm, should the person who owns the car be blamed? Should the company who sold the car be blamed? Or should the programmer who wrote the learning algorithm be blamed? Or who? What if an autonomous weapon decides to kill someone without any human intervention? Who is to be blamed? How do we avoid this? And how do we have systems in place that avoid these kinds of things? I don't have any answers to these questions. But I think it's important that we as a group think about this. And we are especially in a good place to think about this because we understand some of the technical stuff behind it. So we can actually bring in some expertise. All of this together falls under the umbrella of fairness, accountability, and transparency in machine learning. We need to ensure that our algorithms are fair. We need to ensure that our algorithms are held accountable, and we need to ensure that our algorithms are transparent. All of these are super difficult and open questions, but extremely important. And I think we should not think of it fairness, accountability, and transparency as a band-aid that comes on top after everything is done. We need to keep these concerns in mind at every step along the way. When we define a task, should this task exist? In the definition of the task, are we accidentally doing something that will make the classifier systems that come out at the end problematic? When we collect data, are we collecting data that is representative of the way in which the system is going to get used? When we define evaluation, same question. When we design features, when we choose our models, when we choose our learning algorithms, at every step along the way, it's important to keep these concerns in mind. If these things are interesting, there is this growing community that's trying to think about these questions. This community includes people from computer science, but from philosophy, from ethics, from many different communities that previously really didn't talk to each other, that are coming together, from law, for instance. And there are these annual conferences that are held. If you're interested, check this out. This is a question that, honestly speaking, we need as many perspectives as we can get. We need diverse perspectives. We need people to be involved in this all the time, and it's important. These are important questions. Let me now start unrolling the clock, so to speak, and take a retrospective look at the class. In the beginning, in the first lecture, I showed this definition of machine learning from Tom Mitchell. And I said, learning is generalization. A program is set to learn with some experience with respect to some tasks, according to some performance measure, if its performance in the task as measured by this performance measure keeps improving. Learning is generalization. If there's nothing else that you want to take from this class, this is the important thing. Learning is generalization. Memorization is not learning. We saw different kinds of models along the way. Models are just another name for hypothesis spaces, for hypotheses, or classifiers, or generally functions that the learner should explore. Learning is search over functions. What functions is the learner looking at? We saw linear classifiers, decision trees, different kinds of nonlinear classifiers, ensembles of these things. And all of these are really expressing some assumption about the underlying concept. There are different learning protocols out there. We pretty much only looked at supervised learning, where a teacher supplies a collection of examples and the learner has to learn to label new examples using this data. We did not look at unsupervised learning, where there's no teacher, there's no labeled examples, the learner has to go figure something from the data using unlabeled examples. This, if you're interested in this, I would encourage you to sign up for the data mining class next semester, or a clustering class when it's offered, because that's really what it's going to talk about. Ideas from unsupervised and supervised learning together contribute to what's called semi-supervised learning, where the learner has some labeled examples and a lot of unlabeled data. We looked at different kinds of learning algorithms. Online algorithms where a learner has only one labeled example at a time. In the prototypical example of an online algorithm is perceptron. Most of our time is spent on batch algorithms where the learner does something with the entire data set. So SVMs, logistic regression, decision trees, all these ensembles, nearest neighbors, neural networks, they're all batch algorithms. So most successes of machine learning today have been with batch learning. A question that we kind of skirted around, but not directly talked about is how do you represent data? What's the best way to represent examples for a particular task, which involves choices about what features and such things? We didn't talk about dimensionality reduction, but there is some material on the class website. If you're interested, take a look at it. The whole class was kind of scaffolded by this theory of machine learning. We tried to repeatedly define learning formally, and different ways of defining these defining learning gave us different algorithms, different perspectives. We looked at online learning, we looked at probably approximately correct learning, we looked at Bayesian learning, and each of these begat different learning algorithms. There are a whole collection of ideas here. This is a picture from a paper by Pedro Domingos, where there are questions about representation, there's question about evaluation and optimization. We looked at k-nearest neighbors, SVM, logistic regression, decision trees, neural networks. Primarily, we focused on accuracy. And in terms of optimization, we have basically only looked at gradient descent, but there's a whole bunch of other things that we did not see. But it seems like a large collection of ideas. But I'm going to argue that machine learning is actually a little too easy. And at this point, some of you might think I've lost my mind. It's a diverse collection of ideas, but it's amazing how surprisingly equally well many of these things work. And that's something that's kind of a nice unification. You can try a whole bunch of things, but SVM or logistic regression or average perceptron roughly is going to do about the same if you tune the hyperparameters correctly, for example. So there's something fundamentally cool about this point. There are a whole collection of ideas that talk about how learning as a concept works, and all of them seem to roughly agree with each other, and that's really nice. We did not see vastly overpowers what we saw. We didn't talk about kernels or unsupervised learning, about hidden Markov models, conditional random fields, multi-class classification, topic models, structured models. But what we did see was the foundation of how to think about machine learning. If you're interested in these things, there are many other classes that you can take in the next semesters to follow up on this. There's going to be a class on data mining in spring. There are classes on deep learning that show up every now and then. There's going to be computer vision in spring. You should think about data visualization and topology of data and such things. You can specialize into sub areas of machine learning like deep learning, structured prediction, and other things. And there are many such classes that are offered not just in computer science but across campus. So if you find any of these things interesting, I encourage you to look at those classes. In this class, we looked at the underlying concepts and the algorithmic ideas in machine learning. It's not about any one specific machine learning tool. It's not about any one specific machine learning paradigm, but it's about how to think about machine learning. What we saw was a collection of learning paradigms and many different algorithms. Through your homeworks and your project, what you learned was the ability to implement these things. In some sense, if you think about it, through your homework, you really built a tiny machine learning library, which is really cool. And through your, hopefully, both in projects and homeworks have given you some hints about where machine learning can be applied and how to make the most appropriate decisions with respect to all those different knobs that we have to consider. I hope this has been an educational experience for you. I'd like to stop. I want to thank you all for the privilege of giving me the privilege of teaching you. And if there are any questions, I'll be happy to take them. Otherwise, I'll hope to see most of you around, definitely in the exam, but also beyond. Thanks.